Hi, good morning, good afternoon, good evening to everyone, and thank you for joining us for this presentation on why D-mode, and specifically D3GaN for automotive applications, in the Power Conference 2020. In these slides, I will go over the various GaN technologies and explain what D3GaN means for our company, as well as give some application examples from the automotive field. My name is Elijah Bunin, and I'm working as a technical sales and product manager at VisIC for about 6 years now. Over the years, GaN devices have promised a plethora of features over a broad range of applications, from low voltage point of load, LiDAR and chargers, to power supplies and industrial and automotive high power applications. It promised higher efficiency, higher power density, while providing lower system costs. And GaN delivered. We already see commercial products in the market, with GaN inside bringing the promise to reality. When looking at the available GaN products in the market, it is possible to classify them into two base technologies, E-mode and D-mode, with each having their own advantages and fields of excellence. E-mode devices have a simple single-die configuration and are similar to silicon MOSFETs for paralleling. The D-mode devices, on the other hand, can be separated into two additional groups, the well-known cascode structure with a standard silicon gate drive and the direct gate driving topologies. VisIC D3GaN technology is based on direct gate driving. This scheme has additional auxiliary silicon circuitry for safe normally off operation. This topology combines the gate robustness of the cascode structure and the performance of E-mode. Among its advantages are lower switching losses, as only the GaN die participates in any switching operation, high threshold voltage, and standard silicon gate drive. As such, the D3GaN stands for Direct Drive D-Mode Gallium Nitride. VisIC has chosen the depletion mode gallium nitride technology due to its proven and reliable gate structure at high drain voltages. For several years now, D-mode gallium nitride has been qualified for automotive applications, surpassing the AEC Q101 tests at various vendors. Its main advantage is the robust gate structure, as can be seen in the graphs below. You can observe that in voltage gate stress tests, D-mode gallium nitride devices can survive at much higher gate voltage stresses. The operation of the D-mode gallium nitride is generally from negative values, such as minus 15 volts in off state, to on state at 0 volts. In both positive and negative gate voltages, D-mode exhibits much larger voltage margins. The goal of the D3GaN driving scheme is to provide a safe normally off switch while keeping the GaN die switching performance. It consists from the GaN device and two p-channel silicon devices. When no auxiliary gate voltage is present, both of the silicon devices are turned off and the switch is in off state exactly like a cascode. If high voltage is applied to the drain of the D3GaN switch, voltage increases on its in-series p-channel source, which in turn increases the negative voltage on the GaN gate. When this voltage reaches about minus 8 volts, which is the GaN threshold voltage, the GaN device turns off and blocks the entire voltage. However, when auxiliary 15 volts are applied, the silicon devices are turned on and remain in on state during the entire operation of the switch. As such, they do not add any switching losses and act as very low ohmic resistors. If the auxiliary gate voltage fails or the system is turned off, the switch turns into a normally off device, similarly to a cascode. VisIC has chosen the automotive as its main market and developed technologies specifically suited for motor inverters, onboard chargers, and high-power DC-to-DC applications. D3GaN embodies not only the driving scheme, but also the proprietary technology that was developed by the company over the years. VisIC is demonstrating advances in both GaN die technology, packaging for high current efficient switching, as well as application-related features such as short-circuit protection. One of VisIC main target applications is the electric vehicle motor inverter. Using D3GaN, it is easy to parallel devices for high currents by using standard silicon drivers as well as by its inherent capabilities for thermal balancing. The company targets high current GaN products and has demonstrated hundreds of amp switching capabilities, with new higher current products soon to be released. All VisIC developments are optimized for fast switching capability, which can help reduce switching losses in a variety of packaging forms. And of course, for such hard switching application, a high threshold voltage helps a lot for noise immunity. On this slide, you can observe a comparison of tests and simulations done by a top-tier OEM, which was kind enough to allow us to present their findings. The graph in the center shows losses for an inverter using IGBT technology, and the one on the right is using VisIC D3GaN. It is quite evident that by using GaN technology, it is possible to reduce the losses over the entire operational range. This is enabled by the significant reduction of switching losses using VisIC GaN technology. On the left, you can observe a comparison of switching losses taken from similar devices in RDS(on) and voltage rating. For high currents, D3GaN has significantly lower switching losses compared to any other wideband gap technology. And this directly translates into drive cycle savings. The evaluation of this slide was performed by a top tier 1 company and looked at WLTP drive cycle losses comparison of silicon IGBT, silicon carbide, and VisIC GaN technology. This evaluation considered 150 kW of inverter peak power running at 500 ampere ms, 65-degree cooling temperature, and switching at 10 kHz. The results show that wideband gap technology has a clear advantage with less than half of the silicon losses with VisIC GaN, showing even higher power savings. These savings can be then converted into lower battery cost, lower cooling system volume, and overall lower weight. One of the main requirements for the motor inverter is short circuit protection capability. To address this, VisIC has developed a short circuit protection scheme, which is based on sensing current slew rates over the in-series P-channel silicon MOSFET, here marked as RS. This pulsed current sensor has a derivative output together with a bandpass filter, which results in a robust detection method even in fast switching environment. On the right, you can see the half-bridge evaluation board on which this circuit was tested on. The small transformer and logic circuits take minimal PCB space and can be easily implemented. Once this scheme detects abnormal current slew rates, the GaN device is safely turned off in a multi-gate voltage step approach in order to avoid high drain voltage spikes. Additional information can be found in a paper by VisIC on ECCE 2020 titled Short Current Protection Circuit for Automotive Motor Inverter Applications based on GaN transistors. For testing the developed circuit, we followed the AQG 324 standard. And here you can see an example of a shoot-through situation. The low side device is turned on into high voltage, while the high side is shorted using a low inductance clip. As can be seen from the yellow drain voltage waveform, the device saturates almost immediately, and the circuit detects and turns off the GaN in less than 100 nanoseconds. Today's motor inverters can require hundreds of amps. To showcase how D3GaN can meet these requirements, VisIC has developed a demonstration board with multiple parallel GaN switches. Using this board, one can observe uniform switching of the parallel array, as well as run this board at high power to check the thermal balancing of the gallium nitride. In general, GaN has a positive resistance temperature coefficient and is very resistant to thermal runaway. In addition to inverter, D3GaN technology exhibits significant advantages for the onboard charger application as well. Lower losses coupled with the isolated package removes the requirement to parallel devices for 7.2 kW systems. Using this package, total thermal resistance from junction to liquid cooling can be reduced to well below 1 degree per watt. Low losses of the D3GaN can enable hard switching PFC topologies to operate at hundreds of kilohertz. The reference design VisIC has developed in the past shows power density increase possible with 200 kHz switching at the PFC, even while the GaN devices are cooled through the case and not directly placed on the cold plate. As always, a high threshold voltage of above 5 volts helps in achieving the mentioned performance. VisIC is focused on lower DSON high current products, with the 18 milliohm device available now and the 7 milliohm device will be released for sampling in the first quarter of 2021. As previously mentioned in the presentation, all VisIC package offerings are designed to maximize switching performance and current output capabilities. The company offers die and high-power discrete components and is working with selected customers on specialty modules with advanced features. For summary, when looking to implement a wide bandgap technology in your application, it is important to choose the one that best fits all required parameters, from performance and reliability to ease of use and implementation. VisIC is developing GaN technology for electric vehicles. There are many more advances coming from VisIC in the future, so please stay tuned to the various media outlets. I thank you for your attention and look forward to discuss what D3GaN can do for your application.